Hey Prof, last time we talked about dissolving ionic solids, in particular sodium chloride, in water. And I get it that there's a competition for the ions on the surface of a crystal. For example, with a sodium ion on the surface of a sodium chloride crystal, it's positively charged and there's this competition, forces of attraction from the negative chloride ions in the interior of the crystal, trying to resist dissolving, and the polar water molecules pointing their negative ends towards the sodium ion and trying to pull the sodium ions into solution. And the opposite is the story for chloride ions. I get it that since we can see that sodium chloride is soluble, we can conclude that the attractions from water molecules win the competition. In the case of an insoluble salt, the attraction from the ions within the crystal must win the competition. What I don't get is why some salts are soluble and some, meaning that the water molecules win, and some salts are insoluble, meaning the interior ions win, and how we can predict whether a particular salt is soluble or not in water. Fine, Ozzy. Yeah, let's talk about that. But first, let's remember that there is a force, if you like, a driving force called entropy. There's a natural tendency for all things to mix. So if there were no forces of attraction, then sodium chloride ions would mix with the water molecules, and we'd say it's soluble. That's if there were no forces of attraction. But that entropy is not the only factor. There is the energy associated with forces of attraction. If there are forces of attraction, to break them, we have to use up energy. And when they come together, we get back energy. So the forces of attraction between an ion on the surface and the oppositely charged ones inside resist separating and dissolving. What factors do you think affect the strength of the force of attraction between oppositely charged ions, like say a sodium ion on the surface and chloride ions within the lattice? Oh, we did that in Physics 101. The factors are the magnitude of the charges on the ions and the distance between the ions. And the equation was that the force is equal to Q1 times Q2 divided by D squared. Okay. The charge on one of the ions times the charge on the other ion, and decreasing as the distance between them gets bigger and bigger. So let's concentrate on the charges. What might that mean when we're considering the forces of attraction between oppositely charged ions in the lattice in different salts? For example, let's compare, say, sodium chloride, magnesium chloride. So what? Well, we'd be comparing the forces of attraction between chloride ions and sodium ions, and chloride ions and magnesium ions. Sodium ions Na1+, magnesium ions Mg2+ charge. So obviously the attraction of the chloride ions to magnesium ions would be larger. It would be harder to separate magnesium ions from chloride ions than sodium ions from chloride ions. That looks pretty obvious. Good thinking. In fact, we've got some experimental data to back up what you've said. We compare what's called the lattice energy, the energy required to pull apart all the ions in 1 mole of sodium chloride into a vacuum, not into solution, compared with the energy required to pull apart all the ions in 1 mole of magnesium chloride. So what we're talking about is, for solid that, for 1 mole to form sodium ions in the gas phase and chloride ions in the gas phase, compared to magnesium ions in the gas phase and to chloride ions in the gas phase. I've got some data here. This is 788 kilojoules per mole to pull apart 6 by 10 to the 23 of sodium ions and chloride ions from each other. For magnesium chloride, you suggested to require more energy to pull those apart. Indeed it does, 2528 kilojoules per mole. A heck of a lot more energy is required to pull these apart than to pull those apart. Aha! Well, we know that water molecules win the competition, the tug of war, in the case of sodium chloride. And that's how much energy is required to pull them apart before they go into solution. This is so much bigger that I guess there's every chance that the attractions between ions on the surface, magnesium ions on the surface and chloride ions inside, or the other way around, is so much bigger that I wouldn't be surprised if the attraction of the ions within the lattice to the surface ions win out and magnesium chloride is insoluble. In fact, it's so much bigger, I'd expect that to be the case. Ozzy, your logic is fine and your prediction has got some sense about it if the only thing that happens is the pulling apart of the ions in the crystal. But in fact, that ignores another important energy term, the energy that we get back when these ions interact with the waters of equation around them. They'd be attracted to each other from the ion charge and the polar end of the water molecules. Negative end of the water molecules, positive end of the water molecules. So water doesn't just hang around receiving passively these ions into it. Water is a very integral, participating part of that process. So how do you think that the forces of attraction between sodium ions and the waters of equation compare with the forces of attraction between magnesium ions and the waters of attraction, the waters of equation around it? Well, again, because of this equation here defining the strength of forces, I'd expect that magnesium ions would have a much stronger attraction. There'd be a much stronger attraction between magnesium ions and the negative polar end of water molecules than between sodium ions and the negative end of water molecules. This interaction would be the stronger one. Well, you're right again, and we've got experimental data to back you up. We've got estimates of what's called the energy of hydration, or the enthalpy of hydration of these ions. For 1 mole of sodium ions with water to form Na plus equated, I have again the data, 393 kilojoules per mole. For magnesium ions with water to form magnesium equated ions, we get back 1900 kilojoules per mole, a lot more. So in comparison with sodium ions, more energy is needed to separate magnesium ions from chloride ions in the lattice than to separate sodium ions. But when the dissolution process takes place, we get more energy back when the equation process happens for magnesium than for sodium ions. So the high charge on magnesium suggests, because of this force of interaction, that magnesium ions are, compared to sodium ions, more resistant to dissolving, but because of the equation process energies, we get back more, and this makes it more likely to dissolve. So how do we know which one of, in the case of magnesium chloride, whether attraction to the water molecules wins or attraction to the ions in the lattice wins? Well, in fact, Aussie, we don't know. We just can't make that prediction by looking at the formula. Your question's a good one. How can we predict which of these are soluble or insoluble? But we simply can't predict that. In the case of sodium chloride, the energy required to separate them is not very much, and the energy we get back is also not much, but coming back there somewhere. In the case of magnesium chloride, much more is required to separate them, but we get much more back. And just from face value of the formula, we can't tell. What's important is how close this is to this line. Sometimes it's below, sometimes it's above. If it's a little bit above, that means that more energy is required. But remind you again, there's also the entropy effect already making dissolution a natural tendency. So we just cannot tell from the formula. So we just need to know our solubility rules. Well, my answer is partly yes. You do need to become familiar with them, but I wouldn't call them rules. They are not rules. Sodium nitrate is not soluble in water because of a rule that nitrates are soluble. We know that nitrates are soluble by experimental observation. And then the statement, all nitrates are soluble, is just a characterisation, one entry in the list of observed solubilities. It's purely a list of solubilities, and not rules. Then I guess the best way is just to become familiar with the substances. I don't need some list of characteristics of the football players in my favourite football team to know which one is which, what their strengths are and their weaknesses are. I have just become familiar with them, with those players, and I know. Say that again, Aussie, and again, and again, and again. I love to hear it. That's a great perspective, and you said it far better than I could have. Thanks.